Last couple of classes, we've been talking about Fourier analysis. We learned how to implement discrete Fourier analysis through matrix algebra, through NumPy, vectors, matrices, and linear algebra. And we looked at some examples of Fourier analysis. In particular, we looked at the example of Fourier analysis of a damp-driven pendulum. Today's class and next few classes, we're going to turn to the topic of random numbers and random processes. More specifically, we're going to, in this class, talk about the calculation of random number sequences. And then in later classes, we're going to talk about various random processes, random physical processes. So we're going to apply our ability to generate random number sequences to various different random processes. Just like Fourier analysis, it's kind of a ubiquitous tool in physics and beyond. Random numbers are a ubiquitous tool in physics and beyond. Today's class, we're going to focus on an approach to generating random numbers, to calculating random numbers with a computer program. And we're going to also focus on tests of random numbers to test the randomness of the calculated random numbers with our program. So that's the plan for today. Just as a background, our interest in random numbers and simulating random processes covers both what I would call truly random processes and random numbers and seemingly random numbers, random processes. So in physical processes, there are truly random physical processes, and then there are seemingly random physical processes. And classic examples of those two are radioactive decay. Radioactivity is a truly random process. Radioactive decay, radioactivity obeys quantum mechanical laws, and it's truly a probabilistic process and a random process. On the other hand, Brownian motion. The Brownian motion is, for example, the motion of a pollen grain in air, or a smoke particle in air, or a dust particle in air. That's a seemingly random process. So the motion of the pollen grain or the dust particle or the smoke particle in air is determined by deterministic laws of physics, but to calculate the motion of the pollen grain or the dust grain in air, you would have to specify not only the initial conditions for the dust particle or pollen grain, but the velocities and the positions of all the surrounding air molecules. So it becomes as a practical matter, a random process, because it's, as a practical matter, not a calculatable process, although it is ultimately a deterministic process. So that's truly random, radioactivity, classic example. Seemingly random, Brownian motion, classic example. Yeah.
Is sort of like calling something a radioactive decay random, is that sort of like necessarily stipulating the Copenhagen interpretation of quantum mechanics?
I don't know the answer to that. So let me say that, so supposing I had some radioactive particles, right? I'll take muons as radioactive particles, right? A collection of muons as radioactive particles. They have a lifetime that's 2.2 microfarad. So I know their lifetime very precisely. But for any one of the individual one of those muons, I can't say exactly what time it will decay. And I know that about 2/3 of them would decay 2.2 microseconds because I know the lifetime. But for any one, I can't say when or whether it will decay at some period. I don't think that statement is directly related to Heisenberg uncertainty principle, which might be a relationship between how well you can know the position and the momentum of a muon, perhaps, or how well you could know the energy and the time for a muon. So I think my answer is no, but I'm not absolutely sure. I think the argument about probabilistic versus deterministic is that doesn't matter about Heisenberg and the certainty principle and positions and velocities. I wanted to say a little bit about the uses of random numbers. I actually saw that somebody's figured out how many random numbers are used per day by the human population. And I think it was the scale of 10 to the 18 random numbers a day is what we're consuming as a population. So a huge number of random numbers. Random numbers for us are used, for example, if we wanted to simulate radioactive decay, we would use random numbers. We'll do that. If we wanted to simulate Brownian motion, we would have to generate random numbers, and we'll do that too. So those are two examples of physics simulations that involve random number sequences. And a lot of physics simulations involve large numbers of random numbers and random number sequences. And actually, the computer calculation of random numbers and random number sequences really started with physics problems, and it started originally in the Manhattan Project, I think. So physics is a big, and science and engineering and economics are big consumers of random number sequences. But another big consumer is that every time anybody uses their credit card, there's random numbers being generated so that the credit card data can be transmitted securely. Online games, online gambling are all consuming huge numbers of random numbers. And so behind the scenes of the modern kind of computing world is a modern consumption of huge numbers of random numbers. So being able to generate random numbers is big business. Here's a few specifics about what we're going to mean by random numbers and what we're going to mean by random number sequences. So random numbers are numbers picked from a set, complete set, say, of possibilities. So an example would be tossing a coin. The possibilities are heads and tails, and random choices in that case are selection of either a head or the outcome of either a head or a tail. So those, we would use random numbers for simulating coin toss. Likewise for rolling a dice. For rolling a dice, the complete set of numbers are 1, 2, 3, 4, 5, 6, and random dice rolls would be equal probability selection of those from that complete set of outcomes. So 1 or 2 or 3 or 5, 4 or 5 or 6. And likewise for another example would be playing cards, right? That would be a selection from 52 playing cards of with equal probability. We would use random numbers for simulating that. So that's the meaning of a random number in terms of a a number picked with equal probability from a total complete set of possibilities of numbers. A random number sequence is just a change of random numbers, consecutive random numbers, in which the sequence of random numbers that the consecutive numbers are independent of one another. So the next random number doesn't depend on the prior random number, and so on and so forth. They are mutually independent random numbers in a sequence of random numbers. So if I roll two, if I flip two coins, one and the other, whether the second one is a head or a tail is independent of whether the first one is head or tail. That's a random number sequence. If I roll two dice, the number I get on the second roll is independent of the value I got on the first roll. That's another example of a random sequence, and so on and so forth. In physics, we typically in physics simulations of physics problems, we're generating millions or billions of random numbers in a random number sequence. We don't want the next random number in that big sequence to depend on the prior randoms. Okay, a few general words and a little bit of terminology about computer generated random numbers and other ways of generating random numbers. So the first point is that computers are designed to follow instructions. And so it's strange or perverse to ask computers to generate random numbers, because they're really designed for very deterministic following of instructions that they've been given. So how are they going to generate random numbers? How on earth would a computer generate random numbers? Well, we'll see what possibilities there are for computers generating random numbers. Pseudo-random numbers is the term we use for random numbers that are generated by equations, by formulas that we might use on a computer, or we might calculate by hand. So those are pseudo-random numbers. And truly random numbers are random numbers that are generated in physically random processes. And so those are two classes of random numbers. One we can calculate with equations that we might apply on a computer. Another one which are just due to random processes that we can't directly apply on a computer. There's a big difference between the two. The pseudo-random numbers will always repeat. So pseudo-random number sequence will always be a repeating sequence, because in a pseudo-random number sequence, although the random numbers may appear random, if you have a particular number that you start with, let's say we started with 21, is that random number. If we generate a sequence of random numbers and then we get another 21, then after that it's going to generate the same sequence again. And then we get another 21, and we're going to generate the same sequence again. So pseudo-random number sequence will repeat, and it will repeat and repeat and repeat. And our job is to make the period of that repetition, if we want to make numbers that look random, these pseudo numbers that look random, we better make the period of this repetition large, very large as possible. Yes.
So would that, like, those mathematical equations just be extremely non-trivial, like really crazy looking math?
No, actually, no, that's an interesting question, actually. But no, you don't know. We'll see in a moment how to make equations that will make pseudo-random numbers that make a long chain sequence of pseudo-random numbers. But the equation is not complicated. But there is a method to the equation that you'll see. Anyway, so that distinguishes the pseudo-random numbers that are calculated by an equation from the truly random numbers, which don't repeat, don't have a period, which are the arise in physical processes. So just to be clear, we'll be calculating what's called here prings, pseudo-random numbers. We can't calculate with equations the trings, which are the truly random numbers. Okay, this is a rather slide, but I tried to put actually kind of the answer to your question about, how might you go about calculating pseudo-random numbers with some sort of recipe, some sort of formula, some sort of equation on a computer. And so this is sort of an outline of the basic process for calculating a sequence of random numbers on a computer. So I'm going to stand here because I want to kind of read them off and go through them step by step, and I can't remember them all. But remember, our goal is to simulate a sequence of random processes, and good examples to think of are the coin flipping, the dice rolling, or the card drawing. Those are everyday analogies to the physics simulations, the physical processes that we want to explore. The outcomes of coin flips, so whether it's a head or a tail, or the outcomes of dice rolls, whether it's a 1, a 2, a 3, or 4, or 5, or 6, or the outcomes of drawing a card from a pack of 52 cards. We can generate those outcomes from a generation of a floating point number that ranges from 0 to 1. So that's going to be a starting point. When we want to generate the heads and the tails in a sequence, when we want to generate the dice rolls in a sequence, or the cards we draw from a deck, what we're actually going to generate is a floating random, pseudo-random floating point numbers from 0 to 1. So that'll be the heart of whether it's a coin tosses or dice rolls or card draws. We're always going to generate floating point numbers from 0 to 1, and that makes it generally applicable, right? Whatever you're simulating, whether it's the decay of a collection of muons, or whether it's the Brownian motion of dust particle, you'll be drawing from floating point numbers from 0 to 1. So that's the second point. Those floating point numbers that range from 0 to 1, we're going to obtain those floating point numbers from 0 to 1 by actually generating integer random numbers that run from 0, that's kind of the lower bound, up to, I'm going to just call it M, I think, on here. That's the higher bound, and that's going to be some large integer number. So we're going to generate actually integer numbers from 0 to M, and then we're going to divide by M to get our floating point number from 0 to 1. The reason for that is that integers and integer arithmetic, adding integers, multiplying integers, that's kind of native to a computer, to a binary computer. Floating point numbers are not so native to the computer. They're built on top of native computer operations. So we're going to work with the native integers to generate our random numbers. So that's the next step in our plan. We're going to actually generate random numbers from 0 to n, and then convert those integers into floating point numbers from 0 to 1. We're going to do it with, next select, native or basic, in that case Python, in other cases computer operations like multiplication and addition and so forth. And again, we're going to do that because those native operations are kind of a native, that's the language of the computer. That's the language of binary computers, is to multiply binary digits or add binary quantities. So we're going to work with the native operations. That's going to help us with the problem that we want to generate large numbers of random numbers. We got to generate 10 to the 18 a day. And so we want to generate them quickly. Got to generate a lot every second of time. So we're going to use native operations. The scheme for generating the sequence of random number. Remember, we don't just need to be able to generate a random number. We need to be able to generate a whole sequence of random numbers for typical uses. Is to use we're going to use some sort of equation, some sort of formula, some sort of recipe, but it's got to be a repeating equation that we can use on a starting random number to calculate the next random number, on that random number to calculate the next random number after that, on that random number to calculate the further random numbers, and so on and so forth. We're going to use a recursion relation for calculating the sequence of random numbers. So whatever our equation is, whatever our formula is, whatever our recipe is, we're just going to repeat it and repeat it and repeat it, using the last random number to calculate the next random number. So that's basically going to be the scheme for calculating sequences of random numbers. One reason for doing that is that often if you are simulating the planet, or you're simulating a galaxy, you want to be able to run the simulation and then be able to run the simulation again with the same set of random numbers. That's useful in debugging, in understanding your code. And so we want to be able to give our random number sequence a seed or a starting value that would enable us to repeat the set of random numbers. And so these recursion relations will allow us to create repetitive sequences of random numbers if we start with the same seed for the random numbers. So that's the reason for doing that. And so here comes the big question, which was your question really. How can we do this with native operations like adding and like multiplying and so forth? So how can we possibly come up with an equation that's going to create a sort of sequence of pseudo random numbers? And I put, the problem is obvious, right? If your recursion relation was to, I don't use addition, I'm going to take the current random number, I'm going to add 2 onto it. So if I start with 1, I'm going to get 3, and then I'm going to get 5, and then I'm going to get 7, and I'm going to get 9. So it's completely not random. I could say, well, maybe I'll try multiplication. So I'll start with a random number of 1. This is my seed, and I'm going to multiply by 2. So I'm going to get 1 times 2 is 2, 2 times 2 is 4, 8, 16, and so on. It's again completely not random. The addition and the multiplication will just generate sort of progressive series of numbers that have a very clear and very obvious pattern to them. So how are we going to get around that? Well, we're going to get around it with the native operations on a computer are addition, multiplication, subtraction, and division. And with the division comes remainders, or remainder. So we're going to use remainders or modular operation as the key in our generation of pseudo-random numbers. So this was recognized hundreds of years before computer generated the random numbers, that with arithmetic, you could generate a sequence of seemingly random or seemingly chaotic numbers by what's called modular arithmetic. And I'll talk a little bit more about modular arithmetic, but it basically uses, calculates the remainder from division by a number. And in that way, because then you get numbers that kind of wrap around on themselves and wrap around in a kind of chaotic way on themselves, you can generate a sequence of pseudo-random numbers. And this was recognized by, you know, some of the great hundreds of years ago mathematicians. Euler, Fermat, knew that you could, with ordinary arithmetic, with remainders, generate sequences of pseudo-random numbers. They didn't really have an application for it. So for hundreds of years, it wasn't used until suddenly Manhattan Project, they wanted random numbers and they realized that it was one way of making random numbers on a computer. I mean, before that, they used to have literally books published of 1 million random numbers and you would look up random numbers. Okay, so this is going to be our plan. We're going to use this native operation, which is the remainder from division, basically. We're going to use that operation because that introduces nonlinearity into the ordinary arithmetic operations on a computer. It introduces chaos into the ordinary arithmetic operations on the computer. And that nonlinearity and chaos that we want to generate our pseudo-random numbers. So we're basically using what's called clock arithmetic or modular arithmetic. And we all know clock and modular arithmetic, like from the face, literally the face of a clock. So modular or clock arithmetic is arithmetic where the integers have a limited range. Like on our clock face, my integers are going to go from 0 to 11. And at 12, they would wrap back around to 0. So that's clock arithmetic or modular arithmetic. So it's modular 12 arithmetic. So for example, in modular arithmetic, 9, so here's 9 hours, plus 4 hours is equal to 1. So that 9 plus 4 in modulo 12 is equal to 1. We've wrapped around within the space or the spectrum of modulo 12 arithmetic. Numbers we got are from 0 to 11 in integer step, and the modulo operation wraps us around in that space, and that's how we're going to bring in the nonlinearity and the chaos to generate random numbers. So that's the basic idea. Let me just introduce a word. You may well know it, or terminology, you may well know it. Congruent is a word that will come up when we talk about specific pseudo-random number generators. Congruent is a word in modular arithmetic. It's when in a particular modulus, say 12, two numbers are equal in that, identical in that particular arithmetic. So for example, 15 and 3 are equal in modulo 12 arithmetic. That's 15 hours and 3 hours is over here on the far right. So they're equal in modulo 12 arithmetic. And that's all that congruent means. And I'm only introducing it because the generators that we will use called the multiplicative congruent random number generator, and I think the linear congruent random number generator. So the word is in there, but it's just a word that's reminding us they're using modular arithmetic, really. Okay, so here's the concrete answer to the question of what is the complicated mathematical formula. This is the formula that's used in multiplicative congruent random number generators. It's this little equation here. In this equation here, xn is, say that in the sequence, think of the sequence of random numbers. xn is the current random number. And then xn plus one is the next random number. So that's the xn and the xn plus one. We've met these recursions relations before. We met in the linear map and the logistic map for rabbit populations and rabbit survival and so forth. So this is another recursion relation, but this is a linear one. And this map says that the next random number is equal to some constant integer a times the current random number modulo f in the modular arithmetic of modulo whatever n is. So that's gonna be the recipe, and that's a pretty simple recipe because that just involves a couple of negative operations on the computer to take the current random number, use multiplication, use modulo operation to calculate the next random number. So this can be done very, very quickly on a computer, very, very efficiently on a computer. We can calculate large numbers of random numbers very, very quickly. It has, let's make a few points about it. It has two parameters, right? One of the parameters is the modulo that you're going to work in. And the other parameter is this multiplier, which is going to be less than the modulo that you work in. Because if you're working in a certain modulo 12, for example, there's no meaning to numbers beyond 12. So it better be less than 12. So there's these two parameters, A and M, that characterize your particular multiplicative congruent generator. So if you were to build one right now, you would pick an A and M for your particular generator. There's one other number that comes in, and this is now I'm going to be a user of your random number generator. What I would do is I would provide the initial seed. I would provide the starting value for the generation of the random numbers. So I would provide what we x subscript 0, that would be the first number. And from that, you calculate the sequence of the following random numbers, x1, x2, x3, x4, so on and so forth. So I have to supply a seed as well. A few remarks about the numbers that we're going to generate. This scheme can generate random numbers. MCG can generate random numbers from 1 to n-1. So it is a bounded scheme. You know the range of random numbers that you can generate. You can generate them from 1 to n-1. Remember, we're going to want to divide by the number of possible random numbers to create that flow. So we've got to firstly have a bounded range for the random numbers, and secondly, we've got to know the bounded range for the random numbers, and that's true here. So actually, in this case, we would divide by n-1 to we would actually, so we divide by n-2 because we're going to make a random number goes up to less than. Okay, so we can generate a known range of random numbers. And it's a deterministic sequence, right? There's nothing indeterministic about it. There's nothing probabilistic about it. Every random number is calculated from the prior random number. So it's a deterministic sequence. Where with the right choices of M and A, we can make this deterministic sequence look like a rather chaotic, pseudo-random sequence of numbers. So that's the goal. And that requires the right choices of A and M. So, you know, the wrong choices of A and M will not create a sequence of random numbers. The right choices of A and M can create a reasonable sequence of pseudo-random numbers. Okay, I was gonna just make, so let's just make this point again, and then I'll go to a computer code, I think. There's two parameters in the model, the modulo and the multiplier. We call them M and A. In practice, we want to make the modulo big because we want a large, broad range of random numbers, or we want a fine structure of random floats between 0 and 1. We want to make M big. We want to make A have a value that will generate all the random numbers or all the random integers from the lowest random integer, which we'll see in a moment is actually not 0, it's 1, up to m minus 1. That's called a full period. If you able to generate every random number in your random number sequence from 1 to m minus 1, you're generating the full period of random numbers. If you made a different choice of M and A and you only generated a fraction of the random numbers between 0 and m minus 1, then that's not a full period. So we want a big value of m, and we want to generate a full period to have a suitable random number generator. So I'm gonna, first 2 points are made here. To do that, typically m is picked as a prime number. A famous example that was used for many years in computer programs was this particular prime here. And A has to be what's called a primitive root of that prime number. What that means is, we know what a prime number is, right? I know that 3 and 7 so forth, a prime number. So I know what a prime number is. I kind of know what this number is. It can't be divisible by some factors other than one in itself. But what's a primitive root? A primitive root of this prime number. If A is a primitive root of that prime number, that if you took A to the power 1, A squared to the power 2, A to the power cubed to the power 3, and so on to higher and higher powers. In this modular arithmetic, taking A to different powers would generate all of the numbers from 1 to n minus 1. So that's what a primitive root is, that A to some power can generate any one of the numbers between 0 and n minus 1. And that's what you need to be able to get a full period.
So can any integer, since it's a prime number, any of the integers between 0 and m can actually qualify as a primitive root, right? If I'm understanding correctly?
Well, they may be a primitive root or they may not. So I can show you an example, actually.
Okay.
One way to figure out is to simply keep calculating A to higher and higher powers and see whether you get all the numbers in the series.
Right.
That's a brute force way of figuring out primitive roots. That's straightforward to do as long as n isn't very large. But if you do that, you'll see very quickly that most numbers are not primitive roots.
Oh. I was thinking, like, since it's a prime number, wouldn't that be a natural consequence? Like, wouldn't A be able to be any?
Let me, yeah.
I'm just thinking that could be a natural
I
consequence.
think you could think of simple examples where, look, here's a simple example. Maybe not.
There are examples right down there.
Yeah, I got a few, these are a couple of examples of where, maybe these are good enough for your question. Okay. These are two examples that I put in the notes where the value of A is not a primitive root. Now, this is, and you're seeing that it's not a primitive root here because it can't generate in a random number sequence, it won't generate all the random numbers in your random number space. I put these two in because they showed a couple of the major flaws that happens in bad choices of A, right? So look at this one, this is the clock face modulus. So it's not a prime, so it's gonna suffer problems. If I choose 6, right? No, so what did I choose? I chose 6 as my multiplier. I started with 3.
Eventually, it's gonna become a multiple of 12, basically.
Yeah, so we go 3, 6 times 3 is 18, right? So we go to 6.
Yep.
Then 6 times 6 is 36, which is 0.
Right.
And then you're trapped in 0 forever. Because once you get 0 for your random number, you can't get out of that in a multiplicative kind of number. Here's another sequence of problem that comes along. You get this is when A can only generate a fraction of the random numbers. It's not primitive roots, so it can only generate a fraction of the random numbers in your space of numbers. So if we went through the exercise again and calculating with the equation, the sequence of random numbers here, you discover that it has a very short period. It just repeats over and over again, this period of numbers. Yeah. Actually, I'm feeling I've got a mistake here, but anyway, I think there is a mistake on that last one. This, maybe I'll do another slide, and then we'll go to the computer code actually, because we got into talking about problem cases there. The stuck in 0, the killed off by 0 is a problem with the multiplicative confluential random number generator. It's a problem that occurs if you pick the wrong multiplier A, you often get stuck in 0. But it's also a problem that somebody could pick a seed value that was 0, and then you're stuck in 0 from the very beginning. There's a slightly more complicated, a very similar version of a multiplicative random number generator that is the linear random number generator that adds a constant to the recursion relation. So now you've got instead of 2 parameters, the modulus and the multiplier, you've got the modulus, the multiplier, and the offset C. This is the new parameter. But the idea is the same. Again, with this generator, you'll create once you pick the modulus, the goal is to generate random numbers from, now you can have 0, by the way, because the constant, you can climb out of 0. You want to generate numbers from 0 to n-1 with a full period where you are able to generate any of the numbers m to minus 1. So again, it depends on the right choices now of A, C, and modulus. So in the case of the multiplicative generator, a correct sequence for a full period is picking n to be prime and picking the multiplier to be a primitive root. So it's a rather simple rule, at least to state. Your modulus is a prime number and your multiplier is a primitive root. Now we've got 3 parameters. We got the modulus, the multiplier, the offset, and the rules are getting more complicated, and rules that are mathematical papers on how to derive them, so they're complicated derivations. So this is a sort of summary of the rules that you would have to apply to pick a linear congruential random number generator parameters, M, A, and C, that give you the full period, the full spectrum of random numbers. And I'm just telling you that there are rules. I don't know how to get these rules, but there are a set of rules for you to base your choices on. As I say, that a reason for LCG versus MCG is because it kills off the problem of getting stuck in zeros. And then here were some examples of cases where the wrong choice of parameters in LCG fails. You get, for example, you can get repeating increments of numbers, or you can get trapped in other numbers. The last one is getting trapped in 21. But I really want to turn to the code, I think, which is where. Yeah. So in this code, all I've got is a set of parameters for either the multiplicative generator or the linear generator, just depending on whether I set the constant C to 0. This is multiplicative generator because there is no constant, but there is no offset, or non-zero. Down here are cases where there is an offset. So I'm just going to generate different sequences of numbers with these recursion relations, the MCG and the LCG, and we're just going to examine the patterns of the numbers that we get out, and to try and explore these difficulties or challenges or getting full periods. So let's just walk through a bunch of them. I'll make this a bit bigger still. So when I run, I'm going to run OR for this because there's a bunch of plots below. It's always going to go to an error that I didn't remove. But when I run OR, I'm going to just be setting some parameters of my generator. So this one is modulo 12, it's the clock. This has an A that's 6. We talked about that, not being good. A C that's 0, meaning this is a multiplicative generator, and my seed is 3. So it's exactly the case that I had in my notes. I set those parameters, so that specifies my generator, and then downstairs here, what am I going to do? I'm going to generate a period worth of numbers in the sequence. So the numbers in modulo 12, there's we've got 11 possible numbers in a MCG because what 0 is kind of a trap. So I'm going to run this, generate 11 numbers, and so I'm going to generate 11 numbers simply by defining an array to hold the 11 numbers. So R is my array that's going to hold the numbers that could contain a full period. And then I'm going to calculate the numbers in the sequence with the MCG recursion relation. So I've got a loop that's going to be a loop over the numbers that I need. And I'm going to walk through that loop and calculate the next random number. Here I'm calling it R with index I plus 1. From the current random number, R with index I, based on the multiplicative formula, because C0, and the modular arithmetic.
Should be C equals 0 for MCG.
I think I did set C, was it Yeah, it should be C equals 0 for MCG. So let's go and check that.
Well, oh, I was just saying in the notes, it says A equals.
Oh, I say down there, A equals 0. Okay. You mean in my comments?
Yeah,
Oh, yeah, you're right. Yeah, absolutely. Thank you. Okay, so we'll run this and we'll come out of this having generated our random numbers. And remember, this was the case I had in my slides. I guess that's why I put it there. In this particular choice of modular, which wasn't prime, so we broke one of the rules for full period, and 6, which is not a primitive root, check, it can't generate all the random numbers. And random number sequence is 3, 6, and then a whole bunch of zeros will detract from loss. So that's a case that doesn't work very well, but it illustrates my code for calculating random numbers. Downstairs here, I've got a bunch of plots that will become more interesting. So the first plot is the values of the random numbers that I generated. Well, I generated a 3 and a 6, and then I got a whole bunch of zeros, so not very random. Here is the frequency of the random numbers that I generated. Well, I generated 1, 3. I generated 1, there's something a bit up with the scale here, but it's 1, 6. And I didn't generate any other numbers. I'm not counting 0 in here. So, and I got one more plot I'll show you later on, but we're going to make these plots. So that was a short period that was terminated in zeros, which is the trap for MCGs. Here's another set of numbers. This one has, again, it doesn't fulfill the full period conditions. M is not prime, for example. So if I run this, here's my sequence of random numbers, and this is one where that value of the multiplier is not a primitive root. It can't generate all the numbers in the space of 10. So modulo 10 has a space of numbers from 0, which we know is a trap, so we don't want that, but from 1 to 9, but this is only generating these odd numbers, 3, 1, 7, and 9, and that series just repeats over and over again. So that's not a good choice. But the last one here, so this has a modulo 11. So now this is a prime. It has a multiplier, which is 7. If that's a primitive root, it will give us the full spectrum of numbers. And again, it's an MCG. So here's our set of numbers that we generated. And if we look in here, we should have every number from 1 to 10, which are the full spectrum of numbers, avoiding the 0, which is the trap. And this is modulo 11, so we can't have numbers bigger than 10. And this, if we choose this random number generator, you would generate this repeating sequence of these random numbers. 2 would generate the 3, and then we go on to do this again and again and again. So this one has met the sort of basic conditions that we expect. We've got a full period, so we've generated all of our 10 numbers in our space of numbers for that modulus. That's what this plot shows the sequence of random numbers. It was 3, 1, 7, and so forth here. And this plot, oh, I didn't run off. This plot shows the distribution of those random numbers. So we got one of each of them, from 1 to 11. I got a couple of examples down here of the LCG. So now this has an offset to solve the 0 problem. So this is, I conveniently changed the order. They're writing out the parameters here, and then it's dyslexia. My modulo on all of these three cases that we'll look at is 32. Okay, so a good condition for a linear congruential generator. It doesn't require that the modulo be prime. It was a more complicated condition. All of these are done with 32. Let's run this first case. So this is where the multiplier is 1 and the offset is 1. You might be able to imagine what's going to happen then. So run that cell. Actually, let me run all the cells. So here's the sequence of random numbers that I generated. The equation was A times the current random number plus the offset. The multiplier is 1. So it is the current number plus the offset. The offset was 1. So it just adds 1 onto the current random number. If I start with 7, I'm just going to incrementally count through the random numbers, and then I'm going to wrap around when I get to 32, the modulo. But look, this is another good choice. This is another problem that can happen in these random number generators. You get a very linear sequence of random numbers. I'll show you another flaw. This is the same modulo 32. I'm starting at a different value, seed value, but now I've changed my multiplier to 4. So I'm not going to get stuck in that linear sequence. And if let me run all. Oh. Here's my sequence of random numbers. Again, not very random, but this sequence, there's another track that I got stuck in. I got stuck in 21. Because 21, when you calculate with that multiplier and that offset, and in that modulo of 32, you get 21 again. So that becomes another trap. So these linear congruential generators can have periods that are not full periods. We've seen an example of that. They can have traps that are not the zero trap that we saw in the multiplicative random number generator. So traps still exist, actually. Here's a case that fulfills all the conditions required for full period in a linear congruential generator. This has a multiplier of 5, not 4 or 1. And my offset is 1. My modulo is the same. And if we run this case, let's run it all. So down the bottom here is my 30. I got modulo 32. So I could have I printed out 31 random numbers here. And I think I'm gonna do a little more, but I think we got every number, from 1 to 31 here. So we get a full period. And if we make a plot of it, here are the sequence of random numbers, right? It looks pretty random to me. So it does, it is showing that with the modular arithmetic, using a modulus, this wraparound can solve the problem of the simple progression of multiplication or addition and introduce a nonlinearity through the wraparound and introduce chaos through the wraparound that starts to generate random numbers. It looks like random number sequences. So look, this is the first case I think I've shown you where I've generated some sort of more than a handful of random numbers that looks kind of random. If we look at the number times each number occurred, so this should be from 1 to 31. My scale has got messed up. These are the 31 number, and we generated each one of them once. And that pattern would then repeat if we generated further random numbers in the sequence. So it is a repeating sequence that will repeat every 31 random numbers. So we're getting a full period, but it is only a period of 31 random numbers. So that's why in practice you've got to pick a modular value. No one will pick a modular value of 11 or 32 because you don't have a sequence of more than 11, 10 or 31 random numbers. You need a big number. Okay, so those are a bunch of examples. Let's actually look at a case that was one of the earliest random numbers generated. This was out of Manhattan Project. This linear congruential generator with these parameters for generating random numbers. So here, look, the modulo is this big prime number. So this is important in practice because we want a big number because we want to make a whole spectrum of numbers. This number down here is a primitive root. Powers of this number can generate all the numbers from 1 through to 1 less than the prime number. So this is a combination that obeys our rules for MCGs. And this is just our seed. And here you see the 0 this is an MCG, not an LCG. I gotta make one, yeah, I gotta make a change here. I don't want to generate 2 to the 31 random numbers because the class would never end. I'm just going to generate 256. So this is a tiny, tiny, tiny fraction of the spectrum of random numbers that this would generate. And let's run all. So look, here's our 256 random numbers. So I can't see a pattern in it, but it is a bunch of numbers that were generated by this simple recursion relationship of multiplying in modular arithmetic. And we've got a chaotic set of random numbers. So it's really nice to see how that emerges out of basic arithmetic operations. This is the sequence of random numbers that I generated. So here's the first random number. This was 47. And then I went up to 256 random numbers. And these are their values. Well, the range of these numbers is from 0 to 2 to the 31 minus 1. 2 to the 31 minus 1 is larger than 2 billion. So it's more than 2 billion possibilities here, and I've only generated 256. So I've only generated a couple of parts in a million of the possible outcomes of throwing this dice. But look, I got a sort of random scatter or random numbers. So quickly we are learning how to make random number generators that look pretty random and scattered, using the chaotic wraparound nonlinearity of modulo arithmetic. That was the real trick. Let me run this. For some reason it crashed while it's doing that. I don't know why. Oh, I know. There's something else I've got to fix. Okay, so I jumped from trivial examples where the biggest modulus I had was 32. So the biggest range of numbers I had was 30 to 31, and making a histogram of that to a modulus that was 2 billion. And my program is crashing now because I'm trying to make a histogram with 2 billion bins. And I think I'm eating up Google's memory or whatever. And so I'm going to change my histogram. I can't have when I bin the incidence of each random number. That's what I was doing with this small modulo. I was binning the incidence of every random number in the random number spectrum. I can't do that now because I've got 2 billion possible random numbers. I'm going to have coarse bins and look at the distribution. So let's run all. Here's my distribution of random numbers as a histogram. So across there, here, this range here are, I think I got a couple of hundred bins or something like that. I'm looking at the contents of those bins. Now, each of those bins, supposing I had a couple of hundred bins, I've got more than 2 billion possible numbers. So most bins are gonna not, if I've only generated a couple of hundred numbers, most bins will be empty. And most bins are empty here. There's then some bins that have one number was generated in that range corresponding to the bit. And then really occasionally I've got 2 or 3. So that's the distribution. And again, it kind of looks like a random distribution. So at this point, we might be getting pleased with our, we were inspired to use modulo arithmetic by, I don't know, Fermat and Euler, to create a chaotic zero series of numbers. We learned that you have to make the right choices of the parameters in your recursion relationship in this modular arithmetic, so that you don't get short sequences or you don't get zero or non-zero traps. We learn about that, but now we're really generating large collections of what look like random numbers. And for the history of computer-generated random numbers, this was a great success, right? And in the 50s and 60s, we're very happy with these multiplicative, congruential random number generators and linear random number generators for generating sequences of random numbers. But there did emerge a problem. I don't think we'll see it on this one. It's related, but we're going to talk about it in the next one, in the next class, is that if you were to plot the next random number and the current random number on a scatter plot. So this is a scatter plot where the horizontal axis is xn, current random number, and the vertical axis, actually, this is, say, the current random number or the previous random number, and this is the current random number. So 2 consecutive random numbers, and each dot is is a pair of consecutive random numbers. Make a plot like this and we fill it with a lot of data. We haven't filled it with much data yet. You start to see a structure emerge. And the structure that emerges is that beneath this sort of chaos and nonlinearity that the modular arithmetic is causing, you are still using multiplication or a linear equation. And these, in a plot like this, you'll find planes emerge. You'll find that the numbers fall on planes. The planes can be densely packed or loosely packed. And so that was a problem that wasn't realized initially in these number generators, and then was later found in these number generators. But we're going to talk about that a little bit more in the next class.